So now we can continue with our physics section. Let me see the hierarchy I wanted to go through. So I will start with the EOS document first. Okay, let's go through that. Deliverables, I have updated it here in the note section. When you go here, NS, EOS and MR, and then we have this document. Okay, let me just download it. Okay, so far we have covered Welechka model, mean field model. I gave you the code, a minimal code, which is not properly constrained, but I just wanted to demonstrate you how to calculate mean field solutions and how to calculate equation of state using Welechka model, right. So that model was only for symmetric nuclear matter, but today we are going to talk about a model which can also give us equation of state which is beta equilibrated and also charge neutral. What does that mean? The equation of state which is of neutron star. You know, neutron star is a charge neutral entity, gravitational body, and it is also in beta equilibrium, right. So in the previous section we learned how to compute equation of state for symmetric nuclear matter where number of neutron is equal to number of proton. But in the context of neutron star, we know that number of neutrons are way more than number of protons. That is why it is isospin asymmetric system, and the neutron star is charge neutral. So therefore the net electric charge must vanish. There should be some other particle which should compensate the protons, okay, which is very obvious. And the neutron star is in beta equilibrium. That means the weak interaction processes such as like beta decay, they must be in equilibrium. Like the rate of conversion of neutron to proton should be equal to the rate of conversion from proton to neutron. So they should be back and forth equilibrium, in equilibrium, okay. And we know that like after supernova explosion there is a full journey of a like a newly born neutron star like proto-neutron star to the final state of neutron star which is in beta equilibrium. And from the supernova explosion the neutron star is at very high temperature which eventually cools down, and what carries its energy outside is the neutrino, okay. So after a long time like 10,000 years of time roughly speaking, we get the current state of neutron star which is effectively at t is equal to 0 MeV and is in beta equilibrium. So we can extend Welechka model or any mean field model to include electrons so that we have charge neutrality, and also in original neutron system we have electrons, and we can also impose some additional constraints corresponding to these physical conditions. So first of all, what are the particle contents we are interested in right now? So before we had nucleons in our system, neutrons and protons, they were degenerate, but this time we also have leptons in our system, electrons. Optionally muons, muons are heavy, they can also contribute to equation of state at high chemical potential, but for simplicity we can just ignore them for now. And there should be some beta equilibrium condition that we can give in the code, and it can give like it will put some constraint, some specific constraint on the equation of state. And according to beta equilibrium condition we have chemical equilibrium under weak interactions. So the chemical potential must satisfy the following relation, that the chemical potential of neutron should be equal to chemical potential of proton plus chemical potential of electron. And if muons are included, the chemical potential of electron is equal to the chemical potential of muons. So let us not worry about that, we are not considering muons this time. And what about the charge neutrality condition? The charge neutrality, as I explained, the total charge of the system must vanish. That means number density of protons should be equal to number density of electrons. The number of particles protons, the number of protons should be equal to number of electrons, so that the positive charge particle and negative charge particle, the net density is 0. okay, and we are not considering muons, so I will just write it like this, like number of protons should be equal to number of neutrons, okay. So that is a very important equation which will help us constrain our system for neutron stars. And next is, like, we already have nucleonic interaction through the Velechka model. It interacts through sigma and omega mesons, but when we talk about leptonic contributions, they are treated as free relativistic Fermi gas, okay. Electrons, the mass of electron is 0.511 MeV, which is very less in comparison to nucleons. So we can ignore the interaction effects in that. So how do I calculate the number density of electrons, energy density and pressure? So these are the, like, the similar expression which we had for nucleons, if you remember this one, okay. But the only difference here is the m star is not m star anymore, it is just m. So what was m star? M star was m star is equal to m minus g sigma sigma. That means how the effective mass changes with respect to the medium. Medium is what? Sigma and omega changing with the chemical potential. But in this case m star is not m star, it is m, only the vacuum mass, that is the only difference. So that is for free relativistic Fermi gas. And why it is called free? Because it does not change with the medium, it is free all the time, it is non-interacting. So these are the expression for density, electron density, leptonic density, energy density and pressure, and this is the corresponding Fermi momentum we can calculate. Now if we put that these conditions like beta equilibrium condition and charge neutrality condition in our Velechka code, somehow we model our entire thing, then we will get an equation of state which is beta equilibrated and charge neutral. And we already have En and Pn from the Velechka model previously. We can just add, we can solve all the system altogether with new constraint, and we can add the energy density of electron and pressure of electron to the whole equation of state. From that we get something called pressure of total like nucleons plus electron. Now it is a full neutron star system, okay, and similarly energy density of total. Okay, so now we have energy and pressure. So we have something called pressure and energy which can be seen from this plot, okay. From doing all this stuff we get something like pressure versus energy density, and you can see it is softer in the beginning and it becomes stiffer when it goes up with the energy density. The more it leans towards energy density, it is softer. The more it leans towards the pressure, it is stiffer. The more stiffer equation of state is, the more is the maximum mass of the neutron star. This is very much correlated, okay. So this is the equation of state for different configuration. Let us not talk about the different configuration, let us just focus on one line. You can choose any line, okay. So this is what we get from the neutron star equation of state. Now our next step is to calculate the mass radius curve out of it, okay. So before that, let us touch base what is TOV equation, okay. So the TOV equation is named after Tolman, Oppenheimer and Volkoff, and I have shown its derivation, implementation and application here. So the introduction is, like, the TOV equation describes the structure of a static. So there are some assumptions. Spherically symmetric, static, that means no rotation, and the matter inside the star behaves like a perfect fluid. These are assumptions, but in ideal case neutron stars are not necessarily spherically symmetric, they are not necessarily not rotating, they always rotate, the frequency could be different. The matter inside the star behaves like a perfect fluid, which is also an assumption. It might behave like a perfect fluid in the core, but not entirely. Okay, so the TOV equation is based upon general relativity and it is essential for modeling compact stellar objects such as neutron star from the general relativistic extension of the classical equation of hydrostatic equilibrium, okay. Now we start with the metric of static spherical symmetry. So this is the metric. So I'm not going to talk about like all this stuff. I will mainly focus on the equation of motion, the TOV equation. So this is the stress energy tensor, again general theory of relativity, and we get the Einstein field equation where general theory of the stress energy tensor is related to these G mu nu, and from these equations and using the metric, we get two main equations. One is the mass function where the mass is associated with the energy density, and one is the TOV equation which relates the gradient of pressure with respect to obviously radius to pressure as well as energy density. So what we are seeing here, we are seeing two macroscopic quantities and two microscopic quantities. What are the macroscopic quantities here? Mass and radius, m and r. And what are the microscopic quantities here? Pressure and where epsilon, which is the energy density. Okay. So the thing is, if we know the microscopic composition of a system like the pressure versus energy density, we can use TOV equation, we can put that information in TOV equation and we can get something out. We can get some mass and radius relationship. Okay. So if we have some microscopic information of the system on the left side, we put it in the TOV and we get something mass and radius. How do we do it? Like it is not magic, right? There should be some steps. So first of all, you can see the equation of state we got so far is with respect to pressure and energy density. It is pressure versus energy density. It has no information about radius, but in order to put that in the TOV equation, we need pressure in terms of radius, energy density in terms of radius. Okay. So we need to convert our equation of state to a stellar structure where we can get pressure profile in terms of radius, energy density profile in terms of radius, and the output, which is mass profile in terms of radius, total radius, and mass profile at that particular radius. Okay. So how do we do that? We do that again using the boundary condition. We know that at center of the star the pressure is maximum and at the surface the pressure is 0. So we use that trick to calculate the equation of mass radius profile of a neutron star. For example, how do we do that? So let us choose one equation of state here, which is let us say blue. Okay. So obviously the pressure is 0 here, that means I am talking about the surface of the star, and here the mass of the pressure is maximum. I am talking about, for this particular curve, I am talking about the core of the star. Okay. So I get some profile, some radial profile here, 0 to r goes from 0 to maximum, whatever it is. Okay. I get some radial profile. Now I just have to think. So I divide my equation of state in number of pieces. Number of pieces means if I do this as a scatter plot, like if I do it as a scatter plot, I have like numerous point here. You have to assume with me right now. So there are number of points. So let us say there is 1 point, there is 1 point, there is 1 point, there is 1 point. So I choose one point here and I consider it as my maximum pressure. Okay. When I consider this as a maximum pressure, that means the maximum pressure is where? In the core of the star. In the core of the star, I would call the central pressure, or in terms of energy density, I would call that as central energy density. So I am going to repeat that. I took one piece of this curve. From here I assume it has a maximum pressure, and I called it as a energy central energy density and central pressure. So I construct a star profile. This is my P versus P as a function of r and energy density as a function of r, because r is maximum here and r is 0 here. So, for that particular curve I put that information in my equation of TOV equation, and after solving that I get a point. I get a point here, somewhere here, let us assume. I only get a point here, just one point. And similarly I repeated that process for like various points in this energy density, pressure versus energy density curve. I pick this point again, this point again, this point again, this point again, this point again. So, for each equation of state I am changing my central energy density. I am creating a different points in the MR diagram. So, point, we have to think in term of scatter plot, point. So, these are like, this is not a single continuous curve. I am representing it in Python, it is a line plot, right, but actually what code is actually doing, it is giving us the data points like one point at a time. So, for each piece of equation of state I am getting a point, and when I combine all those points I get something called MR curve, and the maximum point I get, like I am interested in the maximum. So, I hope this is the maximum I am getting. So, I conclude that from this particular equation of state, for this blue one, I conclude that this is the maximum mass that a star can hold for this particular equation of state. Okay. So, this is how we do things, and we have a continuous curve. Okay. And this tail shows the corresponding crust. Okay. So, if we have crust in the star, the tail will start from the right, and we have this corresponding curve. If we do not have crust, it will start from here. I will show that. Okay, so, this is how we construct MR profile from the equation of state. Okay. If you have any doubt, I have also put some mathematical information here, but I do not think there is a need to discuss. But still, if you have like some question, I am happy to answer it. But before that, I would just like to conclude that like this mass radius relationship helps us understanding the stability of neutron star, and this data can be compared with the observational data like from NICER or gravitational waves. For example, these bands are from NICER, these two bands are from NICER, and we see our equation of state fits well into the error bar here, and it can explain the two solar mass neutron star. And what were the composition I was having? I was having hyperons and nucleons. Okay. So, the conclusion is the TOV equations provide a powerful way to explore the macroscopic property of compact star from microscopic models of dense matter. So, the accuracy of the solution depends heavily on the quality of the years used. So, this equation of state is from the chiral mean field model, and this is the corresponding output. So, you can use different models to get equation of state, and your TOV solver is always the same. You can always add corrections, perturbations, but it will give you the curve, and that is how you test whether your EOS model is working good or not. Okay. So, this was about like what is a TOV equation, how do we calculate mass radius curve from the equation of state. So, now I will stop for 1 minute if you have any questions. Okay. So, I guess you understand everything. Now, let us jump to the real coding part. Before that, I just want to talk about MUSES a bit, so that you have an idea what is MUSES. Okay, I hope you can see my screen. Can you say yes? I cannot see the Google Meet.
Yes, sir.
Okay, thanks. So I will give you a short introduction about Muses. This is a big presentation, like 56 slides. I will not touch everything. So Muses. So Muses stand for Modular Unified Solver of Equation of State. Okay. So and the PIs are from Kent State University, University of Illinois Urbana-Champaign, and University of Houston. So it's a multi-institute collaboration thing, and I was a postdoc at Kent State working with Veronica Dixheimer. At that time, I was working in Muses, and I am also a part of Muses now. Okay, anyways, I just wanted to have a short introduction about Muses. We already discussed about this thing, the problem we are having whenever we wanted to describe the QCD phase diagram equation of state. Like there is no single model that can cover physics of the entire QCD phase diagram, right? Some model works in this regime, some model works in this regime, some model works in this regime. So we have to depend upon different theories and model. So as a scientist, since we cannot construct a single theory to describe equation of state of whole QCD phase diagram, we need to depend upon different model, and as a scientist we want to club them together, right? We want to get the equation of state from one piece, second piece, third piece, and we want to club them together so that we can have a unified equation of state. So this is our goal. Okay, and I'm not gonna bore you with this. We want to get a unified equation of state, as I told you. So we have different things we can use: perturbative QCD at high density, high temperature, lattice QCD at high temperature, low density, and all those things. We can also get info from de Havilland collision. So what is Muses? So the name stands for Modular Unified Solver of the Equation of State. Okay, so this is an open source cyber infrastructure, and it is a community driven ecosystem that provides computational tools to promote, transform, and support groundbreaking research in nuclear and astrophysics, as well as computational relativistic fluid dynamics, gravitational wave, and computational astrophysics. So basically, in short, it is a cyber infrastructure which is open source, like anyone can join, and it provides a few computational tools where you can go and look for your particular code you are interested in module, and you can play with it, you can get some physical insight, you can publish papers, right? So it has different packages. Okay, so the Muses equation of state has like so many modules. As I told you, like we need different modules to calculate the equation of state of a QCD phase diagram. So I will only talk about CMF module here. Okay, I'm not gonna overwhelm you with all those things. So CMF module is, you can say, the advanced version of Velechka model. Okay, some people might not like this, but okay, it is a advanced relativistic mean field model. Okay, which is also chiral, and we can explain stars, we can explain finite temperature, we can also explain magnetic field system through this model. Okay, and we are going to use CMF model, and we will be doing we will be neutralizing and beta equilibrating it using Lapton module on top of it. Lapton module is like adding Lapton to the system so that we can get a neutron star equation of state. So we are going to use CMF plus Lapton, and then we are going to use synthesis module, which will plug everything together. And on the right hand side we have Muses observable package, which gives us the mass radius module. Okay, so we have equation of state on the left, we have right TOV solver, and from that TOV solver, which is a part of observable package, we can get mass radius module. Okay, now so how does it works? Basically, user input something, there is an input file, you change your input, and it goes to equation of state module, right? The equation of state module solve for that particular configuration, input configuration, and it gives you some output like pressure versus energy density, and then that pressure versus energy density go to a particular observable module, and whatever you are interested in, let us say mass radius, and then you get observable output. Okay, now how does the workflow work? So, we start with the CMF, we put it into Lepton. Why we put it into Lepton? Because CMF is for symmetric nuclear matter, right, and we want it to be neutron star neutralized. So, we add a layer of Lepton. Lepton module does something like it put constraints on beta equilibration as well as charge neutrality, and it gives okay, I got a reminder. 15 minutes, where was I? Yeah, then we have like different modules, let us not talk about that. Then we get an equation of state which goes to synthesis. Synthesis also another module which basically combines two different modules. So, if we do not have any other models, we can just skip this part, and we can also work on the synthesis like only this part. So, what are the goals? Okay, let me just touch base here. So, what we want to do is we have a calculation engine, okay, and calculation engine is like a supercomputer where you can submit your job, and we also have a job management system that you put your job on the cluster itself and you can track, okay, and it is scalable and highly high availability deployment system. It is scalable, like you can run an extensive code there, it is not a problem. Okay, and we have updated our codes to the modern programming languages so that we have an optimized version of the code with the minimum runtime. So, this is the power of Muses. And who are the developers? The team is from various institutes, mainly from UIUC, KSU and UOH, okay, and users can be anyone who is interested in that. So, the beta release is already done, and this is open source and it is public to anyone who is interested in. Okay, so there are several modules. One is the CMF. CMF is particularly used to describe the QCD phase diagram. For example, the white spaces I am talking about, which cannot be explained by the theory itself, fundamental theory. CMF can help us explaining that. Okay, and it can also explain the neutron star matter. So, there are several other modules like crust DFT and chiral effective field theory. I am not going to talk about that, we will just focus on CMF. Okay. And similarly, we have heavy ion collision modules as well, which can describe equation of state at finite temperature, which is beyond this particular internship. We have in observable module, we have Climber. Climber is a TOV solver. You give your mass and your pressure and energy density to Climber, and it gives you the output. Okay, this is how it works. So, yeah. So that was all about Muses, a brief introduction. I can talk about this for an hour, but I don't want to bore you. I just wanted to give you some motivation, like what is Muses, right? So, let us go to the website of Muses, like if you want to explore more. So, you can log into the website. For example, this is the website. Okay, you can log in, you can search Muses Illinois, and you can see, you can read about everything whatever they are offering. So, if you go to code packages, so this is a particular website where everything is written about coding and the structure, everything. Now, calculation engine. Let us go through a calculation engine and let us run real equation of state there. Okay, before that, I will like to tell you, okay, this is how the calculation engines look like. Okay, if you are not logged in, it might create a problem. I can do that in incognito. This is how calculation engine looks like. Okay, so I ask you to create ORCID profile and send an access request to the person, and some of you have already done it. If you have not done it yet, please do ask them, please do ask Matthias. Whatever the process is explained, it is already explained in the web page I shared with you. Okay. So, this is the calculation engine web profile. What is a calculation engine? Again, it is a server supercomputer somewhere in University of Illinois Urbana-Champaign, where you can run your code remotely. Not run your code, you can just tweak that particular code. You can change the config, input config there, the code already in the calculation engine, and you can get the outputs, right. So, this is the goal. So, this is how it looks when you log in, and if you have the superpower, like we have granted you access. Let me see how much time I have in this particular meet, maybe 5 minutes. Okay, if you have the superpowers, then you will see something called API token. If they have granted you, you will see API token. I was logged out. Okay, now I am logged in, and you will get some API token. So, you have to copy it, and you do not have to share it. Come on, I shared it on my recording. Anyways, I will think something about it. Yeah, so you can copy it. Also, if you go there, jobs, if you click on jobs, you can see what jobs you have submitted, right. So, it will be shown here, and the time created, like whenever you submit the job, there will be a time associated with it, but you have to be careful. This is in UTC. Okay, so you have to convert it in the Indian time so that you can relate. Okay, so this was a short motivation about Muses, and now we are gonna run the real code. Okay, for that I will create a new meeting, Google Meet link, and it will take like half an hour, I guess. Then I think we are done. We will be done. So, let me just end this call and send the link again. Okay, I think we can continue. So, how many of you have already the access to the calculation engine? Do we have someone here who has the access? Arjun has the access. Okay. Yadav has the access. Very good. Okay. Very well. So, some of the participants do not have the access. So, I will say like complete it today, because you have 5 days to compile everything, get outputs and all those stuff, right? Okay, so be with me carefully. So each and every step is very important now. So what is our goal? Our goal is to execute run a particular equation of state code in the calculation engine which is already there, right? So there are several Git repositories for a particular. So NSF Muses, this is a GitLab account, okay, with multiple repositories. So you can see there are various models. One is CMF module, one is Crust DFT, Chiral EFT, all those things. We are gonna use CMF module in that. Okay, you can also install it locally in your machine. You can play with it. And there is a climber module. Where is that? Newton Star Climber, which is a TOV solver. You can also install it locally and play with it. You can click and you can see the documentation. But this is not, we are gonna do it today because it is a tedious task. All this installation, you know, updating, there are lots of library we have to do. We have a simpler thing, okay. So in the internship, if you are working with me in a project, we can go through like a particular module and we can go through step by step and, you know, learn everything. But in this internship, we are more focused on, okay, what we can learn on the superficial level, so that we can have some understanding, some motivation to do the deeper stuff, okay. So let us start with the EOS of CMF module. So I'm not going to use this here. So what they have created a particular Python Jupyter notebook which can execute tasks for us in a very minimal way, very simple way, okay. So what you have to do, you have to go to the Muses folder, not here. You have to go to the code, and in the code you have Muses folder, okay. Then you will see something called CMF underscore CE underscore tutorial, right? So you have to click on that. When you click on that, it will open it in the collabresearch.google.com. You can open it in Jupyter notebook, you can open it in VS Code, but I will say Google Colab for now, because it is, you know, there are some issues with like when you are linking different things. So I would recommend you to open it in Google Colab only. So you have this entire document here, okay, and you don't have to worry about all these things. You have to just focus on the things you are interested in, right? You don't have to worry about like reading each and every stuff from the whole document. So I will tell you which parts you have to play with, okay. So let us clear all output, okay, so that we have a file from the start. So we don't have any output, okay. Now I will press run all. Oh, before that, if I click a folder here, right, I click a folder here and it is showing me like this, okay. Can I start from the beginning? Run time, read start session and run all. Okay, what you have to do, so this will open like this, okay, and the first thing you are gonna do is to clone the repo. So this is an open source repo, you can git clone it in your system and it will give you like some files, okay, but you need a GitLab account for this, or you can download the required files from the shared folder. So in the shared folder I have already put utils.py, plots underscore util.py, eos.csv and calculation engine api.py, okay. So what you have to do, you have to click here and you have to upload. When you open this, you will not be showing anything like any folder here, downloads, plots will not be here, these 4 files will not be here, only sample data will be here. So you upload this thing here, okay, you upload these 4 files here which are very necessary. I doubt like this is not necessary, but you can run without it, then you can upload, okay. So we need these 4 files in this specific location. This is outside the folder, main folder. This is in the main folder. Okay. So this is the first step you are going to take. So when you upload all the files from the repo to the file explorer left side, okay, then this is a temporary session. You will have to repeat this process every time. So the what is the meaning of that? So if you disconnect this browser, right, and you again started this thing, you have to do it again. You have to upload it again. But I did not disconnect it, that's why it is still showing here. So this download and plot folder will only appear when we are successfully done with the first run. Okay, it will not appear otherwise. Let me just close that and see if it really go that way. I disconnected it and I opened it again. Okay, and I clicked here. Oh, it is again showing it. Okay, it should not show it. So these folders will only appear when we successfully run it, and these are the 4 folder you have to upload it. Okay. Now, can I do it in the incognito mode? Let's see. Oh, it requires an email. Anyways. Okay, the next thing is let us go through. You can read this all this stuff. Okay. So there are multiple cells. You don't have to put like energy in understanding all these things, right? So one thing you have to do when you go down. So these are the libraries which are very essential to run this notebook file, right? So what you have to do, you have to go to your this, right, and you have to copy your API token. Can I change my API token? I am sharing it a lot. Anyhow, you have to put it here, okay, in the quotes. So before that, you can replace it by my API token here. So you replace the API token. Now it is connected to your account, this particular Jupyter notebook. Okay, so whatever you will changes you will do here will reflect in your account here. Okay, so this is the next step, and then you don't have to tweak any setting. Whatever it's written, it is fine. Everything is fine. Okay, you don't have to change anything. Okay, it is a structured process like to execute the jobs. What basically you are interested in this particular data column definition, so that you know whatever output files you are getting, what is the particular column you are interested in, right? What is the first column, what is the second, what is the third, like temperature, baryon chemical potential, strange chemical potential, charge chemical potential, baryonic density, strange particle density, charge particle density, energy density, pressure, entropy, sigma mean field, zeta mean field. I think they are self-explanatory. Delta mean field, omega mean field, phi mean field, rho mean field, all those things, right? So these are the columns which we have to relate. So once we are done with this, you just have to change the API key there, okay, and then you have to press the run all button. Okay, when you press the run all button, it starts executing each cell one by one, and it has started complaining which cell. Okay, I will do run all again. So when we press run all, it is linking, it is installing all the required libraries. Okay, step by step it is executing. It is linking my account to the cyber infrastructure in calculation engine to this Jupyter notebook, and it executed step by step all those things, you know. I will explain this part. And it is complaining here. Why it is complaining? Object is not subscriptable. Which object? Okay, this is weird. let me see if I whatever I did, it is reflecting here or not. 25 6 325. I executed in the morning. I was testing it, but it is not working now. Let me think. Let me do something else. Okay, so this is the same workflow, but I will do it from scratch now. So I will do run all. When I do run all, so it will complain it is running. Okay, it will complain because it is missing some modules. Okay, so what I have to do, I have to upload them. So when I have to upload them, I will upload these files. This there were 4 files, right? Okay. Yeah, so these are the 4 files I will upload. Okay, I uploaded the 4 files, and you will not be able to see the output folders here. Okay, when I did that, I will do run all again. Okay, now it is not complaining about the module. Now what I will do, I will replace my API token. I will replace this getPass.getPass by using my API token in the code. Oh, it changes every time. That is good. Okay. Okay, now this is my API token, the new. You all have your unique API token. Okay, that is, and I can just comment it out for a simpler one, and I have to be careful with the brushes here. Okay. Okay, now I will do run all again. So it has started running. Taking some time. So it is executing step by step, again going cell by cell and executing everything. I hope it is not complaining now at the job cell. Yes, it is not. Okay, it is not complaining. So every cell has a different meaning. So let it execute once, and then we will discuss about it. So now it is executing this. So when it executes, you can see downloads and plot folders, right? When you click downloads, it is still not completed. It has just created that folders. Also in the plot, it is still working on it. Okay, meanwhile it is working, we can go through the cell one by one. Okay, so I am a developer in a particular CMF module, not the entire calculation engine. So my friend Nicholas from UIEC helped me with this workflow Jupyter notebook, where we can access our different EOS code easily. Okay, so this is the minimal version, user friendly, where they can make changes. So obviously you can see this is a dictionary. Okay, define option for the module. So obviously the module have some specific conditions, some specific inputs that we can change and run our modules again and again. So there are like different cases, for example CMF only, CMF baryon, CMF baryons climber, CMF Maxwell. CMF only means CMF with nucleons only, CMF baryons means CMF with the entire baryon octet, like nucleons as well as hyperons. And then we have what we are going to execute is CMF baryon and climber. So what I am going to do is I am going to execute CMF, get equation of state from CMF for the total, where was I? Okay, I'm gonna, yeah, so this dictionary I am interested in, where this dictionary correspond to CMF, which will give me US code for neutralized equation of state, and then I will plug it into climber. Okay, climber is the TOV solver. Okay, and what are the options here? Vector potential 4, like I told you about in a mean field model like Velechka type model, we have vector fields like omega, and they have self interaction, which we did not included in the Velechka model, but in a more advanced model we have something called self interactions, where we can have like omega 3 phi cube or something. So there are like different type of self interaction, and corresponding to that there are different vector potentials. So these are from 1 to 4, so you can change it from 1 to 4. Okay, I will write it 1 to 4, you can change it from 1 to 4, and you can change the label, but I will not recommend you to do that. Okay, CMF plus plus, let it be like that. If you are using 2, then you can write 2, you can change that, but not anything else. Then use hyperons. Do you want hyperons in our system as a degree of freedom or not? If you want like strange particles like lambda, sigmas, cascade, then you can let it true. Okay, if not, you can just write it as a false, and you do not want decoupled, you can also write it as false. Okay, so I want to go with the minimal one, so I will just write false false. Okay, so you can do your changes in this particular cell where you are defining options for the modules. So this is a main dictionary where you control things. Then workflow. So we have 4 options for CMF, right? So I am gonna work with CMF baryons, leptons and climber. Where is that? Yes, this one. So I am interested in this particular function which will execute CMF baryons, lepton and climber. Okay, so what are the input parameters I can change? So they have not provided us the full freedom, right? Because this is a minimal thing we can tweak and learn. If we provide the everything we can tweak, it will be a mess. For example, I showed you my neutron.in file. It has like maybe 50 parameters or something, so I don't want to mess up my code. So we changed this variable in the beginning, vector potential, hyperons, decoupled and all those things. It can fetch that variables from there, and we can also change this, like what MUBI range we are interested in. Okay, I'm not interested in 1800, I can do with 1600. And what is the step size I am interested in, I can change this as well. Okay, and you don't have to change anything. You can change when you feel like you have an advanced understanding, but not right now. So yeah, you can change this value. Okay, and then you don't have to change anything here. So this function is out of our scope, so we were just interested in this particular function, CMF baryons, leptons and climber. Okay, and then we go down, this is like where you launch the jobs. So which dictionary we were interested in this particular dictionary. So it will fetch through that dictionary and it will only launch that particular function, this one only. So this is a Python, I think you can relate, you have a good understanding of all the for loop, list and functions and if else condition in Python, I guess. And then we don't have to worry about that. This is something which we are connecting whatever we are executing in the Jupyter notebook to our calculation engine server. Okay, we are connecting the jobs there. We don't have to worry about anything here. Now this is something technical where we are monitoring the jobs until they are finished and save the result. If the job is executed, it will save the result as success and it will save it in the downloads folder. Okay, so you can see now if I press downloads, we have like so it has executed the job, right? It is a magical box where we put some input and it gave us some output. So let us go through our page here and let me reload it. Okay, I submitted a job. What's the job I submitted? CMF C4 Lapton Climber. I submitted this. Okay, and it also submitted this for some reason. I have to tweak, but we are mainly focused on this thing. Okay, and I can convert this to UTC to IST. Come on, so that you know when I executed this. Okay, so I executed it around 11:06. It started at 11:06. It took some time. Okay, where was I? Here or here? Yes. And what in the downloads folder, what can you get? What kind of data you can get? Okay, so we are not interested in Climber singleton, so I will not go there. So I will go here. So there are different stuff. We have output from CMF in the opt folder. We have output from Lapton in the opt folder. We have output from Climber in the opt folder. CMF is again equation of state generator, a mean field code. Lapton CMF is another layer which gives us the only beta equilibrated and charge neutral matter, and Climber is the TOV solver. Okay, let me just open the outputs here. So this is a hierarchy, organized very well. So CMF output for leptons and baryons, right? CMF output metastable. You don't have to worry about this. You only have to worry about stable one, right? This one and lepton baryons. Okay, and how do you know what is the column? What is the name of the column? You can go through this, define the data columns, and you can fetch that particular data. So this is in a CSV format. I can just open it so that you have a understanding. Okay, so it has a data and the columns are written defined here. Okay, so there are number of data, so I will just focus on this data and this data, and then in the Lapton itself I am interested in the beta equilibrated EOS, right? So if I click on that, the Colab can also open this. That's good. So this is an EOS, right? It has multiple columns. So how do I know which column is what? Again, where was I? Yeah, I will go to the Muses EOS columns. Okay, then what? Climber columns. We have what? Observable.csv. So which is have Climber columns, which is this. Okay, so this is how you know that the data has been generated and it gives you output. It solves the code and it gives you output, and you can relate left to right for column. So now it reads the data files. You don't have to worry about that thing, but you are interested in plots, right? You don't want to look at the data, you are more interested in the plots. So let us do the plotting. I am not interested in that plot of pressure versus energy density, because it is hard to understand it, but I will do the 2D plots here. So in the 2D plots I have to do one setting here. I have to change job 1 to job 0, and then I press this button. When I run the cell, this gives me the equation of state from CMF. So what it is doing, you can see it is giving me equation of state, pressure, come on, it is giving me a pressure versus energy density, right, for different charge chemical potential. So CMF runs over different charge chemical potential. How do we know that? Come on, go minimize. I need to get out of this. Yes. So it depends upon what input you give. You give input baryon chemical potential from 900 to 1800 with the step size 10, and the charge chemical potential you give minus 400 to 10 to 0 with the step size 10. So this is what it is executing. So it is executing this minus 400 to 0, and it gave us the energy density versus pressure for all those mu b's. Now the next thing is you want to understand, okay, what about the equation of state, which is particularly for neutron star matter. This is not for neutron star matter. So for neutron star matter we put some constraints. We put some constraints like beta equilibrated matter and charge neutral matter. When you put that, when you put a lepton module layer on top of it, it gives us a particular equation of state, particular curve in the whole CMF model output, which is neutron, which is for neutron star, which is charge neutral and which is beta equilibrated. Okay, and you can download that from the files. Now this is a beta equilibrated and charge neutral, this particular red line. Now climber will only take this particular line, equations of state, in the top. It will only put this particular red line in the top, and it will give the corresponding mass radius curve. See, I am not executing the cell where I have no interest. For example, I have no interest in energy density NQ and P. I don't want to see that plot. I wanted to see the plots like the neutron star equation of state. Now I would like to see the plots of climber mass radius. So I have to make some changes every time like this, and I press this button. Okay, now it will plot the MR curve. So this is the MR curve. So you can see this is the radius and this is the mass, and what is the maximum mass I am getting? It is around 2 solar mass for this particular equation of state, and it goes like this. I told you, if there is no crust, it will start from here. If there is a crust, it will show something like this, like 2. Now it is only going that way because there is no crust. Okay, so this is how we create a mass radius plot from the neutron star equation of state. Now you might ask me, everything is like going on with just pressing one button. It is not going like that. CMF is an advanced relativistic mean field model. When I change the input, it does everything. It takes like 5 minutes, maybe more, or maybe 2 minutes, I don't exactly remember, but it runs the code. It depends upon how much input parameters, what is the step size and all those things, but it does that thing, and it does that layer by layer. It calculates CMF first. Okay, it calculates all the solutions of CMF first, then it put layer of lepton module, which gives us the particular equation of state, which is beta equilibrated as well as charge neutral, and then it put that output in the observable. So it is interlinked, you don't have to do anything, right? But I have given you some exercises in assignment 3. So you have to download the outputs. For example, I told you about downloading lepton baryons.csv or stable, and you relate it with the column. Similarly, lepton beta equilibrium EOS, you have to plot this. So you get the output from that and you have to plot that and you have to show that in your presentation. Okay, so this is how we run the code in calculation engine, and I will delete the unrelated part which we don't need so that it has a less mess, and I will test my script and then I will share it with you. Okay, I will update the script in the folder. And then you guys can play with it. So what you can do, you can change the dictionary if you are interested. Okay, take hyperons true, take decuplet true, maybe some combination true false, false true, maybe not 4, maybe 3, maybe 2, maybe 1. Just try to improvise. Okay, do something but make a record. And you are not interested in the so I told you about which function, this one, right? So you are not interested in the 940 to 1600, maybe 1800, maybe 2000, maybe 3000. So you can do that. Okay, you can change that and you can play with your code. I will not assign a particular input to person. You can do whatever you want, but make sure you understand how things works here. And you will see the jobs here, like which jobs you have created, and if it is success, then if it is has saved or not, all those things will be here. Okay, so I think yeah, that's what I wanted to tell about this Muses calculation engine. If you have any question, it's time to ask. Okay, I understand you guys want to play with it first and see if it is working or not, and then you have more questions. Okay. So far, okay, for like were you guys able to relate with me, like whatever I was going through? Give hands up or down. Okay, so I will upload the video so that you can revisit that again, and you can execute your code by yourself. Make sure you have the access by today. Okay, request the access and we will do things. Okay, what else? I have just one last thing. Before that, I will just go to the assignment part. Assignment solution, assignments. Okay, so assignment 3. So assignment 3 is your final assignment and the deadline is June 30th, and it is a strict deadline because your presentation is gonna start on June 2nd. Okay, July 2nd. So you will not be getting any extension for that. Submission link is open. So the part 1 is, let us go through here. The part 1 I kept it optional, so you can rewrite my Velechka code from scratch for symmetric nuclear matter and make plots. But you have to do that. Use Muses calculation engine, run CMF lepton climber, and plot mean field versus mu b, effective mass of fermions, particle population. You will get every information from there. I will walk you through that. I will help you. Okay, and I told you about where to get the data, where to get the output, how to use the calculation engine. So you have to spend some time. Then we have a Beamer presentation. Okay, it is self-explanatory, and this change part 2 to an article format in LaTeX, and last push everything in the GitHub repo. Okay, I will do some more changes in this assignment 3 and I will deploy it later today. Okay, so far so good. Do you guys have any questions? How Are things going on? Good, overwhelming?
So that my line has gone in between. So how do you use Muses? Can you please tell me?
Can you say again the first thing?
That line has gone in my home, so just I connected. How to use that Muses website?
Yeah, the Muses thing again. This one was working, right? Yeah. This is an entire video. I will upload it if I explain
First
it
we
now.
need this CMF collaborate, or we can use Muses directly from it.
You just
First
needed
we need
a
this code.
Yeah, you just needed this IPYNY the notebook, and you should open it in the Google Colab. Okay, and in that Google Research Collab you can go
Oh,
through.
then it means without this code, Muses is meaningless for me.
Without this code,
Yeah, if I don't have any code, then how can I use Muses?
you
And
cannot use
like,
Muses in that way. Muses is
oh,
meaningful
okay.
in a sense that, okay, this is open source, right? You go to this, you go to CMF module, okay, you go to CMF plus, you clone it, okay, you clone it. You have to read the documentation, okay, you have to read the documentation, entire documentation, like how to install, how to run, all those things. Like it is written here, it has explained everything here. If you want to do that, you can do that. Okay, this is one way, but we understand the user is not like it cannot CMF itself is a like 1000 line of code, maybe 6000 lines of code. So we have created a minimum version for the users who are not interested in the coding itself, like updating the model itself, but they want to use the model as it is by changing some input variables. This is why we have created this Jupyter notebook, where you can easily link your account to the Muses calculation engine, and you can play with the equation of state modules there. Was that your question?
Yes, sir.
Okay, yeah, we need some interpreter between calculation engine and us, right? And that interpreter is this IPYN by this notebook. So if you have an advanced understanding in Python, you can remove the parts where you are not interested, but make sure the code is still working. Okay, you can remove a lot of if else statements here. So I will try to create a minimum version so that you don't have to worry about all those things.
And last time you have told that we write in C++. So all these written, this is in Python or C++?
This is Python. This is a layer.
Oh,
This is a top layer in Python which is connecting things together. Okay,
okay.
yeah. So when I run CMF, when I run Lapton module, or when I run Climber, basically it fetches the information repository from the GitHub itself, and the code modules are written in C++. In the calculation engine, C++ is running, C++ is executing, but the front layer is in Python. Like we have bash layer, and then we were using bash to execute Python scripts, right?
And you told it will take around in Python 9 to 10 days. Like if you use the supercomputer, does it help in processing power?
Yeah, it does help. For example, my computer takes like maybe 1 day to execute some code. In supercomputer it takes like 1 hour. There is a huge scaling issue, yeah, advantage.
Is there any way to connect with supercomputer, like we also, or we need to be a student of OI University?
Oh, you want to use real supercomputer. I get what you mean. Okay. So you want to submit your stuff, let us say, right?
Yeah, with the university, like we can collaborate in here, Department of Physics we have, but like in international Ohio University like this, can we collaborate with them also?
You have to be part of that institution. I don't think they will give you an access. No, I have an access because I was a part, and I am active in research. Um, so I don't think so. But this calculation engine is something else. This is dedicated for executing these codes. But the other people like Nicholas, he's from Illinois, so he can do whatever he wants in the cluster. But we have some limitations here. You can ask your institute about if they have like some supercomputer access. For example, in US, in each state there is some supercomputer facility like Ohio supercomputer or something, but in India I don't know of it. Maybe in some big institute like Ayuka or something. But in, you're from Nepal, right?
Yes, sir.
So do
We
you
have
have,
in Department of Physics. So,
yeah, so do you have that facility in Nepal?
yeah, I have got two supercomputer in there, and we can ask them.
Yeah, you can ask them like if they can give you an access. The process is same as batch and all those things. You can easily get it. Do you have any more question?
No, sir.
Does anybody else have any question? I have one astrophysics presentation pending and I'm done with everything else. Let me stop the recording first.